I did actually receive another email a couple of months ago. I'll read it out to you. It said, "Dear John, I've just got back from vacation. Unfortunately, I pulled my wade muscle and now cannot walk or even stand properly." Does anyone know what a wade muscle is? Martin? I was very worried for a short while that Martin would not be able to make it, but he's super fit and has recovered from his wade muscle injury very well, and he is now here to give our first keynote. I'm eternally grateful to him for coming. I think he's a huge draw for the conference, and I'm humbled to have him here. So Martin, would you like to come up and tell us something about Dotty? I think we're all very excited to hear.
Thank you. Okay. Let me just connect. Let me see. Oh, I guess. Wait, I have to get my. Okay. Great. Okay. Good. One second. Okay. Okay. Yeah. Okay. Well, thank you, John, for inviting me to Scala World. He didn't invite me first time, so he said he would save it for second time. So I'm very glad here to be finally, after all the good things I heard from the first time. I couldn't wait. I would like to use my talk to explain you a little bit what I've been working on over the last good 3 years now already, and that's really going back to compilers, which is sort of my lifelong hobby and occupation, to think about compilers, to write compilers for interesting languages, and also to rethink the architecture of compilers, and this talk will be mostly about that. So the title of the talk is Compilers Are Databases, and when I gave this talk the first time, a previous version of the talk, people came away with, I believe, a completely wrong conception. They thought it was about storing trees, ASTs on disk or something, like to persist essentially a format which is not source but some higher level format. So that's not what I meant at all. So what I'm talking about here is really in-memory databases, which nowadays most databases are anyway. I think that's sort of the trend in database also. So with in-memory, I mean that I'm interested in the internal data structures that a compiler keeps to essentially reason about your programs, or everything it keeps there, and I'm arguing that the database view of this is a very useful view, and that it's about time we change that. That might look controversial because typically when you talk about compilers, it's something like this, right? So let me just get this. So you have a source program, and then there's a box, and it transforms it into an executable program, and well, that program then it will eventually run. So it's all very boxy, whereas we all know that databases are round, right? So, so are we putting a square peg in a round hole here? So what I'm going to report on in this talk is essentially how we essentially put the square peg in the round hole in the new compiler architecture for the Dotty Scala compiler, which I abbreviate DSC here. So Dotty Scala compiler has, unlike previous compilers, worked on an almost completely functional architecture. That was another innovation, and I'm going to talk about that. And it also uses a lot of low-level tricks for speed, because one of the goals of the new Scala compiler was to make it faster than the original Scala compiler, and so far we seem to be on track of achieving that goal. So some of the concepts of these compilers, like I said, are inspired by functional databases, or you could also say functional reactive programming, because the two really are, again, quite similar. So the ideas of functional reactive programming and functional databases are pretty close to each other. So I've been working on compilers for a long, long time, starting with the 80s. I got into computer science because I was a mathematics student, and I did an exchange here in Oxford, and they have a wonderful bookstore called Blackwell's. I don't know who knows Blackwell's. And they had all sorts of crazy books, and one of the books was about compiler construction, which was a completely unknown book. I didn't really, haven't seen this ever since, but I got this book in my hands as a mathematics student, and from then on I was hooked. So essentially I almost couldn't finish my mathematics studies because I was so hooked on compiler construction, and that's still what I do. So I started with a Pascal compiler in the 1980s, and that became a modular 2 compiler. And all these compilers, they were essentially built with the same idea. They were single pass compilers. That means you read the source from top to bottom, and as you read in your parser, you already produce the final output, the bytecode. Well, at the time we had either bytecode or native code. So it's a single pass through the program, and it just produces the final output. Very, very fast. The problem is there are certain restrictions. So for instance, you can't look at something that is defined after the position you use it. So that is just not possible. You need certain tricks like forward declarations. Also, of course, it was very hard to do anything deep semantically that way. There's still compilers like that around. So Pascal modular 2s are examples. The Go compiler is another example in that vein. And in fact, people from Niklaus Wirth's team are also involved in the Go team. So there's a clear heritage going from one to the other. Then in the 90s, I wanted to build a functional language on Java, because Java just came out, and the big thing with Java was it had a garbage collector, which was like the first platform that made it suitable for a functional compiling a functional language. So I got together with Phil Wadler to design Pizza, and before I designed Pizza as a warm-up, I said, well, there's this new language Java, we better write a compiler for it so that we understand what it is. So I wrote a Java compiler called Espresso. And that, interestingly, again, there's sort of a strand of genetic heritage that became the E compiler. E is a very interesting language about capability architectures, and it now influences quite a lot essentially security architecture of JavaScript through Mark Miller, who was essentially principal author of E. But they took essentially this Espresso compiler and evolved it into the E compiler. And it also became Borland's JBuilder. So those compilers, they were not single pass compilers. They were building an AST, an abstract syntax tree, and at the time they used an object-oriented version of the abstract syntax tree. That meant that an abstract syntax tree has a lot of classes, one for each program construct. So you can say for a typical language maybe around 40, 50 of those. And each of these classes was essentially in the object-oriented dogma self-contained, so it contained everything that you needed to compile nodes of that class. So there was something that essentially a node, let's say, for apply for the function applications, and it says, well, here's how you type check it, here's how you generate code for it, here's how you pretty print it, and maybe several other things more. Turned out that was a bad idea, because to do anything in terms of a new process in the compiler, you had to touch all the 50 node classes, so it was a lot of essentially spaghetti coding and a lot of dispersed changes. But at the time, that was sort of the idea. After we tried that, and I think the result was it was a failure, We changed it then to pizza, which essentially threw out the object-oriented AST in favor of an algebraic data type, essentially. So it was still a hierarchy of classes because that was the only way we could represent it. But you had pattern matching, and essentially you wrote the program in a typical functional structure with an algebraic data type. And that led then to GJ, which is the generic Java compiler. That led to Java C. So GJ was in Java C from 1.3 on. The generics got enabled in 1.5. That led then to the first version of Scala C, which was essentially still written in a pizza-like language, so a Java with plus pattern matching. And that led then finally to the compiler we're seeing today, the NSC compiler for Scala. NSC made was the first compiler bootstrapped in Scala, written in Scala from the ground up, and it made some use of the functional capabilities of Scala. It also added a lot of things. It added REPL presentation compilers for IDEs, like Eclipse and Enzyme, runtime metaprogramming with toolboxes, so the whole Scala macros effort was based on this compiler. But it's fair to say that the architecture of this compiler is really the same as pizza. So essentially all through this sequence, things haven't changed that much. So it was still essentially an AST, which was had some mutable bits in it, and then you did pattern matching, and you had a number of phases to compile a high-level program to a low-level thing. And with the next generation Scala compiler, we tried to, for the first time, to rethink these things fundamentally. So to say, well, is that really the right architecture for compiler, or should we do something completely different? Rethink compiler architecture from the ground up. So that was the exercise. The secondary exercise was we wanted to introduce some language changes with the aim of better regularity, and also with the aim of better language foundations, because the name Dotty comes from essentially the dot calculus, and dot stands for dependent object types. So that's essentially a new calculus that we have proven sound about a year ago, and that has since appeared in several papers. There was a paper at Waddlerfest. There will be a paper at Uppsala about it. So it's now finally a solid foundation for what Scala is, which is really important because Scala is a very sophisticated language, and if you do that without a solid foundation on which it is built, then you are on you build your castle on sand, and it's very, very complicated. So Dot now is that foundation that can explain most of the core features of Scala. That's very good. And Dotty is a compiler that's directly inspired from that calculus. Current status is it's basically bootstrapping itself. We start to compile a set of community libraries. I think one of the first that compiled was Scala Check. We focus a lot on backwards compatibility right now, essentially get more and more Scala code to compile under that. And for that reason, we are getting fairly slowly started only on new language features, because we realize that it's pretty pointless to have a lot of shiny new language features and nobody using them. So we first want to make sure that a lot of people can do a smooth transition into the new compiler before we start to go crazy with new language features, which we will be, but in the future, but not right now. We have grown the team quite a bit. We started with Dimitri and myself, basically, with some small help from others. Now we're joined by Felix Mulder, Fengyun Liu, Nicolas Stucki, Olaf Gerson, and so it's a growing team, and hopefully a growing team will translate into growing speed of getting things done and finished. So what's the architecture behind this compiler? Well, the traditional view of compilers that you've seen in the intro slide was essentially it's just a function from sources to outputs. And we have to typically modify that a bit. It's not a single source with separate compilation. No, we have typically multiple sources. Programs are split into separate compilation unit. And of course, we don't want to compile all these sources together. So what we typically do is we compile some sources, and we take essentially the compiled info from the other sources, which I call here symbol tables, or some serialized symbol tables. And that gets fed into the compiler, and the compiler essentially produces the code, the output, bytecode or native code, And it also produces the symbol tables that we can then feed back into the compiler runs for other sources. Okay, so that's the current established view of what a compiler should do. Now, what are the challenges? I mean, why deviate from that view? Well, I think there's a compiler for a language like Scala faces actually quite a few challenges. Among the most important ones are complexity. Compilers are complex beasts, and we have to somehow tame that complexity. Speed, we all want a faster Scala compiler, so how do we get there? Latency. Latency is not the same as speed. With speed, I meant mostly throughput. How many lines a second can we compile? Latency, I meant if we use the compiler, let's say, in an IDE or REPL scenario, how fast is it to come back with essentially an answer to a question I ask it, like what's the type at this node, or follow this hyperlink, or these sort of things. And finally, reusability. So can we essentially use the compiler basis in non-traditional applications like a REPL, like an IDE, like a meta-programming toolbox. So to what degree can we essentially turn the compiler into a service that can be used, consumed from all these applications? So one challenge is complexity, in particular in the transformations, because our input language, Scala, is far from being a simplistic language. It's quite complicated. The output language, the JVM, is also quite complicated as languages go. I mean, compare, let's say, to lambda calculus as the output language, which I can fit in like a quarter page the definition, or even compared to essentially very simple bytecodes, it's far, far more complex because you have to talk about classes and subclass relationships and constant pools and about 100 different instructions and a lot of essentially high-level concepts that you have to maintain. There's a certain notion of type correctness that you have to maintain in the bytecodes and so on. Okay, so we have two complicated languages, and the semantic gap between the two is actually quite large. Scala doesn't look at all like the JVM, so there's a lot of things to bridge. So if you compare that with compilers to simple low languages such as SystemF or SSA, it's much more to do. And also if you compare to, let's say, compilers that don't do much, let's say, CoffeeScript on top of JavaScript, well, there are some simple syntactic transformations, but it's all not that far away, the gap. But if you go from Scala to the JVM, that's a huge amount of transformations that you need to bridge that. So here's a snapshot. By now, there are more of a previous list of transformations. You see here there's a parser, there's a typer, which essentially adds the types, and then there's a bunch of things which essentially all do a little thing. Elim repeated, I just pick out a couple. Elim repeated essentially eliminates var arguments, which you have to deal with, so it expands them out. Extension methods eliminates or does some parts of eliminating value classes. Tailrec does the optimization, the tailrec optimization. That means if your function is tail recursive, then it will essentially compile that to a while loop. The pattern matcher, well, it will compile pattern matching. Explicit outer will deal with the fact that we can nest everything, but the JVM is flat, so we essentially have to introduce outer pointers for everything. What else do we have? Elim by name eliminates by name parameters, and replaces them with function calls. Erasure is a biggie, so that essentially pulls everything down to the type system of the JVM. So before erasure we have the full Scala types. After erasure we have basically JVM types. And then we have a bunch of things. Mixin does the translation of traits. Lazy vals does translation of lazy values. Captured vars does the fact that some of the variables that you see in a closure have to be boxed, and so on and so on. And finally, you have genbcode, which is essentially the bytecode generator. So those are, I haven't counted these, are about 30. I think by now we have refined this further, and I think we're pushing 60 of those phases in the Dotty compiler, 60 transformation phases. Fortunately, each one of them is very, very small. So A lot of them are maybe one page only. So that's a nice modularization, but it's sort of like microservices, but we have micro faces, so a lot of faces here. So to achieve reliability, we need to have excellent modularity and minimize side effects. Because imagine the nightmare scenario that you introduce a bug somewhere here, and you just produce something which is wrong, and it just goes, and at the end maybe bytecode just explains and dies with an assertion error, or even worse, the verifier dies or the code is wrong. So what do you do then? How do you fix the culprit? You look at these 60 faces and says, well, which one did introduce this thing? So this is sort of really terrible. So you want to put really strong checks in place that prevent you from doing this sort of hunting needles in haystacks. And one of the disciplines there, of course, is minimize side effects, because once you have side effects, then it's very hard to reason about it. Another thing is that we actually maintain very, very strong invariance. So one thing we say, well, after every one of these phases, the program must be a type checkable Scala program. So no violation of the rules allowed. It must still be able to pass the same compiler. And we verify that. So we can turn checks on which say after any phase, we can turn a check on which says, well, erase all the types, retype check the program, you must end up with exactly the same types you must end up with exactly the same tree and types that you got in, and only then we're good. Otherwise, something is wrong and you generated wrong code. And this checking phase called ycheck does many other things that essentially enforce invariance of the code. So that gives us a very strong safety harness to deal with these things. Okay, so that was the complexity. The second challenge really is speed. So current Scala C achieves maybe on my computer, on my style of coding, 500 to 700 lines of code per second. That can vary widely, not so much with the computers, they're all pretty fast now, but with the kind of code that you write. In particular, if you do very, very heavy usage of implicits, in particular deeply recursive usage, well, there's a price to be paid. That will cost you time, and that can slow you down indefinitely. If you play the game, it can slow you down to 1 line a second or something like that if the implicit things are just too deep. The Dotty compiler actually uses a lot of implicits, but they're not super, super deep, so not really predominant uses of recursive implicits and things like that. Okay, so we get about 500 to 700 lines, which is respectable, but not great. Everybody would like it to be faster, but that's very hard to achieve. The first thing is that you have to realize that essentially abstraction and functional programming do have costs. Maybe for an application which is fast enough already or is I/O bound anyway, it doesn't matter. Or maybe you say, well, the standard idiom is to say, well, just optimize the hotspots, right? And that's completely right. So you say, well, don't worry about essentially micro optimizations, don't worry about essentially write your code as nice and abstract as you can, and then you go in a profiler and you find out the hotspots, and those you optimize selectively. And that's absolutely the right technique. Only in the Scala compiler, I don't think there are any hotspots left. There are none. We looked for it. There are none. It's smeared out, basically. The whole complexity is smeared out over everything. So people have tried. There was a group of students, I think from Imperial, who got charged in a project to essentially, the project was to make the Scala compiler faster. And I think there were 5 students or so, and they spent a semester on it. And the result was 0. So 0, no improvement, nothing at all. And that's not very surprising because it's really very, very hard. My biggest frustration curve, I don't have the actual thing anymore, so I drew it, was we had a plot of essentially the bootstrap time of the Scala compiler, and that's about what it looked like. So there were these obvious things where somebody introduced an inefficiency, so it jumped up, and you could pin it to a single commit, and then at some point it would be corrected and go back again. So that was fine. But then there was this slide here, and the slide was essentially just creep of essentially code where more and more code got added and more things. People said, well, let's use a map or a fold here because it's nicer than the other code. And all of that, you say, well, that's maybe a fraction of a percentage point that the whole thing got slowed down. You couldn't even notice it. But overall, you had this thing. It just crept up, and there was nothing you could do against it. So this was really very frustrating. Except maybe say, well, forget it. Code is frozen. No more bug fixes. Speed matters. So you had this point of maintainability and speed. Okay. The other challenge was latency. So some applications require very fast around for small changes more than high throughput. An example is the REPL or worksheets, the IDE presentation compilers, but really also even if you do like use SPT with incremental compilation, then maybe the raw compiler throughput isn't so important, but essentially the ability to react quickly to a change is more important. So we're talking about essentially incremental performance of a compiler. And to make that fast, one of the reasons is you need one of the recipes to make that fast is to keep all things loaded. So that's what SPT does, that's what IDEs do. But even if you keep all things loaded, you have to be smart about incrementality. You can't recompile the world on every time someone wants to essentially integrate a change. And the final challenge was reusability. Compilers have now many clients, not just the command lines, invoked by the build tools, by the IDEs, by the REPL, by metaprogramming. And that's very important. There it's very important that abstractions do not leak. So you do not want to essentially, you want to provide an interface that is very high level and that doesn't expose any of the low level and maybe dirty performance tricks that are in the compiler. And I think there again functional programming helps, and there in particular I think that's where I have to say mea culpa, where we didn't live up to expectations, I think was in the macros. So I think the Scala macros were a clear example where essentially we let too much abstraction leak. We exposed too many details of the compiler, and that means that now we're going to have a really hard time to essentially migrate away from these macros to a higher level called Scala Meta, which is being worked on and which promises a lot. But because we have let all these abstractions out, it will be hard to port, because now essentially a lot of the things that we exposed are things that are very, very compiler specific. Okay, good. After these challenges, what I want to talk a little bit about the approach, about the architecture, in what sense compilers are like functional reactive programming or databases. So let's start with a question. Every compiler has to answer a question like that. Say I have a class, C, with an F here, and at some point in an IDE or something, I change it to the class which now has a function with 2 parameter sections rather than 1. What's the type signature of C.F? So essentially when I say C.F, what's its type? And the answer is, well, it clearly depends when that question is asked. Here you can see it immediately. Well, F, it would first be something like that, and then it would be something with 2 sections. But it's really more fine-grained because the compiler itself translates and transforms the program, as I've shown you. So the time-varying answer really looks a little bit like that, where we said, well, initially that's the type of the function, x colon t to t. After erasure, because t was a type variable, it gets replaced by any. So if the compiler is past its erasure phase, then that would be the view it has of this function. Now we edit, so we go back to the first phase, and we suddenly see a curried function with 2 parameter sections. If we compile it again, let's suppose we have an uncurry phase, which is reasonable to have. So we have 2 sections, it combines it into 1, so it would look like that. And then after erasure, finally, we get that. So obviously the question, what is the type of C.F, doesn't have a single answer. You have to say, well, it depends when you ask, at what period do you ask. Okay, so the naive functional program approach would be like this, where we say, okay, let's just take everything, so all the sources we compile, all the persisted symbol information, everything we look at in the program, the whole program, and translate it into an intermediate representation with a number of phases, and that gives us output. And then somebody changes the world, changes the source file somewhere, and then we do the same thing again, and we do that for every change. problem with that, of course, is how big's the world? So the world is essentially everything a program touches. It could be humongous, right? So it's your program and all its dependencies, basically. And the point is that it is humongous, but typically only a very, very small portion of the world changes at any one moment. So you have to take advantage of that. And in the classical compiler architecture, you don't do that. You just run batch from one to the other. And the classical approach the classical functional approach to see this as a functional transformation would do exactly the same. It wouldn't take advantage of incrementality here. So more practical strategy would be to take inspiration from functional reactive programming and functional databases, where we say, well, we treat every value as a time-varying function. So we say the signature, the question, what is the type or type signature of C.F, doesn't make any sense. We have to say, well, what is the signature of C.F at a given point in time? Or otherwise put, if we would ask that, then essentially we would get a function from time to the signatures there, which will be very hard to compute, and which therefore we won't let you ask this question because the answer to that is too hard to compute. But we will essentially insist that when you ask what is the signature of C.F, you give us the point in time when you need to know, at which you need to know that information. So that means that we need to index in the compiler every piece of information with the time where it holds. Quite a dramatic blow-up of our information space here. So what is time? So time in the compiler is measured in terms of periods. And a period consists of two fields. One is the run ID, and the other is a phase ID. Run IDs are incremented for each compiler run. So each compiler run, you get a new run ID, a new epoch in the time starts, so to say. But epochs can be very short because, let's say in an IDE, you restart the compiler every second or so. Every keystroke could be more than once a second. So epoch can be sub-second durations. And then a phase ID ranges from essentially the first parser phase to the final phase, which is phase 50 or 60 or something like that, depending on the architecture. Okay, so that's essentially the graphical view of your time. So you have these runs, and in each run you have this little box, which is your period, and then you go to the next run and the next run, and so on. Okay, so what do you then see as values? So if you want to say the signature, type signature of C.F, we have to pass it essentially the current time. So you can say at run 1 and phase parser, that's what it is. And at run 1 and after phase erasure, that's what it is. And at run 2, you get that. And at run 2 after uncurry, you get that. And at run 2 after erasure, you get that. Okay, so the task of the compiler then is to compute all values needed for analysis and code generation over all periods where they're relevant. So the problem, of course, is that the graph of this function is huge. So it's even bigger than the world. It's the world multiplied by all the time indexes. So it's a humongous graph of a function, and we need work to make it efficiently explorable. But for a start, it looks like the right model. I mean, that's what a compiler needs to deal with. Okay, so now I want to go into more detail, essentially how this idea of functional reactive programming, time-indexed values, is reflected in the core data types of the compiler. And those core data types are abstract syntax trees, types, so essentially that's the structures that describe types in the compiler, references, denotations, and symbols. And I want to concentrate in particular on the last three because, as we will see, typical compilers use symbols, and in this new architecture, essentially the symbols play only a very marginal role. So one of the big discoveries in the new architecture is that we had to essentially abandon this idea, the traditional idea of a symbol table and symbols that represent information, and we had to relegate to essentially a role which is quite marginal only. But let's start with something which is more concrete, which essentially everybody has a clear grasp of, and that's abstract syntax trees. So the abstract syntax tree is essentially the structure in your compiler that describes your program as a tree in a structured way. So for instance, if you write x times 2, then the compiler would simplify this thing and says, well, that's an apply node, so it's a function application, and the left-hand side is a method call called star. Of course, the compiler will immediately desugar this to x dot star 2, right? So the left-hand side is a selection where the selected identifier is star and the qualifier is x. And the right-hand side is a list, because generally applications can have multiple arguments. So it's a singleton list with a single element, which is a literal number 2, and the tail of the list is nil. So that's just a hand-drawn, quickly representation of an AST like that. Okay, but these trees are pretty useless because essentially they're just the naked syntactic structures. So to do more, we need to know more about these trees, and typically we store that in attributes in the tree. So what about tree attributes? What do we store in the tree? Typically, it's a sort of a zoo of different things that you store there. In DSC, we tried to simplify as much as we could, and we ended up with exactly 2 attributes that we store in the tree. One is the position of the tree. That's sort of something intrinsic that comes with it, and it's not super important for the rest of the compilation. And the other is the type. So you could say there's really one semantic attribute only, and that's the type of the tree. And that's all there ever is. So the job of the tree checker is then to transform untyped to typed trees. So after the type checker, you would have a tree that looks like this. So I have essentially now added for every tree in red the type attribute that I store in that tree. So for instance here I would say, well, the identifier x has type int, and the select node has type, it's a method from int to int, and the literal has type constant type 2, which is a subtype of int again, and the apply node works out that because that type matches that type, conforms to int. So the application is well typed and it has type int. So I store in every node the type of, and that's essentially the result of type checking. Type checking takes an untyped tree and gives me back a typed tree. Okay, so the distinction whether a tree is typed or untyped is pretty important. So if you see a tree, then it makes a big difference whether you can look at the type of the tree or not. And so it merits being reflected in the type of the AST itself. So here I talk about types now in 2 different levels. So this thing means I have some info about what the user level, source program type is. The second type is to say, well, I want to characterize whether a tree has a type attribute or whether it does not have a type attribute. And a good way to do that is just with a type parameter, right? So I could now say, let's make these the same class of trees, but a type tree would be a tree of type, so that means it has a type in its attribute, and an untyped tree would be, would be a tree that has nothing in its attribute. So there is no type. The type of the type is nothing. So there's nothing in the type attribute. Okay, cool. So that means we have a base class like this, tree of t. It has a type field which gives me a t. So that means for a type tree it will give me a type. For an untyped tree it will give me nothing. So that's good. And then I have another thing to turn one tree to another called with type. So I can take a tree, typed or untyped, it doesn't matter, and I essentially add a type to it, and that gives me a tree of type. So essentially we'll take the tree and give me a tree of type. And it's smart about things in the sense that it avoids excessive copying, because it turns out that copying is really one of the performance problems in compilers. So if it goes from type to untyped, then it actually reuses the untyped tree and adds a type. And otherwise, if I add the same type twice, it will again reuse the tree. And only if I essentially have a type tree of one type, and I said, well, now I want to give it a different type, then it will actually copy the node of the tree. Okay, good. So that's the basic tree structure. now we have a question of variance. So should there be a subtype relationship between those two representations, a type tree and an untyped tree? And if yes, what should it be? I guess the answer is, well, there should be a subtype relationship, because otherwise I would have to copy a lot of things that as I add types to trees, I have to copy the whole tree. And that is probably not what we want to do. Which of the two is more useful? Should a type tree be an untyped tree, or should an untyped tree be a type tree? Well, I guess it's clear that a type tree should be a subtype of untyped tree. In that case, widening from type to untyped corresponds to erasure. Forget about the types, right? And it's the more useful relationship, because it just means that we have a tree, we have the type information, and we just forget it. Now we essentially retype check it and essentially do the type checking again or something like that. Okay, so what relationship do the variance rules imply? Well, if I look at just this thing here, then of course I would say, well, types are, trees are covariant. If I look at the whole thing, then actually, no, they're covariant, yeah. So, so we have a problem here that we say our variance relationship here says the trees should be covariant in their attributes, but what I really want is contravariant. So we make them contravariant. There's an unchecked variance. We just put an unchecked variance in there. How can we get away with that? I mean, this is sort of things that I should say, don't do this at home, right? Because usually you get burnt here. So here we have a very, very special circumstance, and we have to argue very carefully why this is defensible. So the reason why it's defensible is that there's an interesting exception related to the bottom type, nothing. So what could go wrong here when I just make them contravariant? Well, what could go wrong is that given an untyped tree, I expect to get a nothing, but I might get a type. So yeah, what can I do with a nothing? Well, I can't do anything. So essentially, I could say, well, give me this thing, and I expect it to throw an exception or to loop, but actually I get a type. I get more than I bargained for, in a sense. So that's sort of the soundness problem that we're exposing with this thing, but I believe that's a soundness problem we can live with. But it's sort of the fact that nothing is special. If it would be, let's say, a tree of object versus a tree of string, and I say, well, given this thing, I expected a string, but I got just a normal object, something else, then that's really bad, because I expect a string, and I didn't get a string, right? But what can you do with a nothing? I expect a nothing, and I got something better than that. You can't do anything with a nothing anyway. So that's essentially the reason why we are getting away with that. Okay, but it's sort of one of the reasons why, even though you shouldn't use unchecked variance, you really shouldn't. It's good that it's there, because sometimes, just sometimes, you need the escape hatch, and that's one of the very, very rare cases where you do. Okay, so then what are types? So types carry most of the essential information of trees and symbols. There are two kinds of types. There are the types that you typically have for values, like int or int to int or boolean, the tuple of boolean and string. And then there are types that you don't write in your program, but that they're still types of definitions, for instance. That's the syntax for the type of a method. That's a type that gives you the lower and upper bound of an abstract type. And class with some info gives you the info about a class definition. And they are represented as subtypes of the same type for convenience. But that we could have done also differently, but it's done that way in the compiler. So if we now look at references to say, well, if we have these nodes like select or ident, what are their types? Here what you see, you just see a name. So how would you find out what its type is? So normally these tree nodes would carry a symbol which acts as a reference to some definition. So you say, well, store a symbol which is a pointer to a definition in the node, and then the type is a type of the symbol. Or here the type is a type of the symbol as seen from this prefix in qualifier. but there are actually no symbol attributes in the compiler for good reasons. So we have to essentially think about something else. Okay, so let me talk about symbols. The traditional scheme is that we have a source and then a bunch of intermediate representations and outputs, and then there's on the side there's a symbol table. So everybody dumps symbols in the symbol table and looks them up, and it's not done in the first phase because transformations might create new symbols and types of symbols might change and so on. But of course that's not very functional. So we need something better than that. So what we again, I want to come back now to the functional reactive idea. So what's the meaning of object.function, so a function in an object? Again, of course, it depends on the period. Does that mean that object.function has different types depending on the period? No, that doesn't work. Trees are immutable. So we can't just change the type attribute depending on the period. That wouldn't work. So we need something that is an immutable thing that persists over time, that can describe many things, essentially different types at different times. And that thing is called a reference. So a reference is a type, and it contains only a name and possibly a prefix. And there are two forms of references, term references and type references. So a term reference is essentially a reference to an identifier, a value, or a method, or something like that. And a type reference is a reference to a type. And they have a prefix, and sorry, this should be name, and a name. So a prefix is essentially what comes before the reference, from which to take it, and that's again a type, and they have a name. And the name is a term name for term refs and a type name for type refs. Okay, so these references, they are immutable. They exist forever. So that's the first innovation, that we have these references. Normal compilers don't have that. They deal with symbols. And a reference is compared to a symbol, it's serializable. So a reference is just a name, and possibly a prefix, whereas a symbol is a pointer somewhere in your table. It's definitely not serializable without serializing the whole symbol table, which is the world, which is not what we want to do. So a reference is something that can stand on its own. So what about overloads? So when we say a reference consists, let's say to a term, consists just of the prefix and its name, then if you have several overloaded methods that essentially live in the same class, have the same name, how do we refer to them? Well, that's actually hard, and it's essentially it's no wonder that overloading is completely universally hated by compiler writers. So every compiler writer, when you ask them which feature would you like to remove in your language the most, they will all respond overloading. Overloading is just terrible, terrible, terrible. It complicates everything. But of course, users are quite happy with overloading, and it's something that users want, and compilers writers have pain providing. So the trick here is to make the scheme work with the references is to allow a signature as part of the term names. And signatures are essentially lists of names of erased types, which is not too different from the way the JVM does it. If the JVM references, let's say, a method, then it's not by its name, but it's by its complete signature string, which is essentially something which contains essentially a mangled version, a serialized version of the type, of the erased type of the method. Okay, good. So now we dealt with references. So what does a reference reference? What does it refer to? Well, surely a symbol? No, it's not a symbol. References actually capture more than a symbol, and sometimes they capture less than a symbol. They capture no unique symbol at all. So let's have a look at that. So consider again my class S, my class C, and we have a prefix which is new C of int. And now I have the expression prefix.f. So that resolves to this definition here, but what's also important is that the type of this prefix.f is not t to t, as implied by the signature here. It's int to int, because I have to essentially take into account this information that the prefix is a c of int, so t is int. So a reference really refers to more than a symbol. It refers to a symbol and a type at the reference, which is not implied by the type of the symbol. Both pieces of information are part of the meaning of prefix.f. And sometimes a reference points to no symbol at all. So for instance, if we have seen overloading, then a simple reference doesn't point to anything. We have to augment it with a signature. Here's another example using union types, which are supported by Dotty and will be in future Scala. So let's say you have these two classes, both have a method f, and we have a prefix which is of type A or B. It's the union of A or B. And then we return either a new A or a new B. And then we write prefix.f. So what symbol is referenced by prefix.f? Could be that or that. So there is no unique symbol that we reference. It's a bunch of definitions that could be the symbol of this reference. So again, this idea that references reference symbols is wrong. So what do they reference? So a reference is essentially what the meaning of the reference is. And for meanings in computer science, we have often the term denotations. So that's what we call them in the compiler. A reference denotes something, and the thing it denotes is the denotation. So the meaning of a reference is a denotation, which of course explains nothing because I just invented a word for it, nothing more. So we have to talk about what the structure of a denotation is. So a denotation, let's have a look maybe first here for the most common case. It could in fact reference a symbol, in which case we find a symbol here. So finally a symbol here. And it got the information which is essentially the type of the symbol as seen in that denotation, which we've seen can be different from the type of the symbol. So it can be a symbol and a type. And sometimes, like in here, like here, the symbol can also be missing, because here we don't have a clear symbol, so the denotation can only give us essentially the type. We could also have an overloaded denotation that says, well, I have a name. It could be several overloaded methods, and in which case the overloaded denotation gives us a bunch of alternatives, which are, again, denotations. OK, so now we have essentially a structure for what references mean. So what then? So finally we got to symbols. What then is a symbol? So a symbol represents a declaration or a definition in some source file. And it lives as long as the source file is unchanged. If I change the source file, the symbol will go away and be replaced by a new one. The symbol has, again, a denotation which depends on the period. So we've seen that with at the beginning of the talk with this method f, which had different types according to essentially different phases in the compiler: erased, uncurried, curried, and so on. So a symbols have many denotations depending on the periods, and the symbol essentially represents a declaration in some source file. So so finally this is sort of an anchor for meanings. So how can we get to the meanings? How do we compute new denotations from old ones? So if you have a reference pre.f, well, essentially what we can do is just recompute. There must be an algorithm to compute the type of f in pre. That's essentially the membership thing. It looks up all the members, it finds out the types. And to find out the new type of pre.f at a new phase, well, just redo the algorithm, look it up again, and you'll find out what that type is. For a symbol itself, a symbol has essentially a denotation, and then you say, well, let's say the f function, and how do we know that after uncurry it has a new type? So there the idea is that the compiler actually has two transformation functions. One is the transformations on trees, so that's essentially the thing that rewrites trees. Let's say in the phase uncurry, it would essentially rewrite a curried function application to a flat function application with a single parameter lists, and the same thing for function definitions. And then there's a denotation transformer, which essentially transforms the denotations of symbols and says, well, if a symbol had this type before uncurry, then after uncurry it will have this type. So in the end, what you have is that a symbol, which is a single declaration, is essentially it's related to a set of denotations which are indexed by phases, so, and which are for convenience arranged in a ring. So you have here maybe one denotation which holds from phase 1 to 3, then another which holds from phase 4 to 4 to 10, and then one which holds from phase 11 to 15 or something like that. And symbols, essentially, the meaning of a symbol is indexed by the actual phase we're in. So the phase is sort of the central clock of the compiler. And to make the lookup fast, it essentially has a cache in here called last denotation. So we check whether the phase is still the last time, same as the last time we looked. And if that's true, then we just follow the pointer, and otherwise we have to search in this cycle to find the right phase of things. Okay, good. So put it all together, what we've seen. As you notice, these things are UML diagrams, which is quite uncontroversial in a functional programming conference, but I think they actually do this job of, in particular, functional reactive programming quite well to actually explain what the data structures of the compiler are. So let's put it together here. So we started with trees, and they have essentially nodes like apply and select, overall maybe 40, a good number, 40 subtrees. So essentially they're an algebraic data type. And trees have a single attribute type. I ignore positions here in this diagram because they don't change anyway. And types, all these arrows, unlike normal UML diagrams, they're immutable unless otherwise specified. So this thing is really a functional database schema. Well, no, yeah, functional database schema. So because a normal database is also mutable, but a functional database is not. Think of it as a functional database schema. Okay, good. So trees have an immutable type. Now types are again another ADT, which is, there are things like refined type for refinement, named types we have seen. And those types, some of those types, in particular named types, which act as references, they have denotations. Oops, sorry, oops. They have current meanings, right? And here there's a P and a star, so that says that thing is actually time dependent. So the denotation of a reference changes with respect to the phase you're in and also with respect to the run you're in, because a new run might give you a new definition for a named reference, and therefore it would change. Okay, so a denotation always has an info, which is a type. So we go back here. And it can be a single denotation or a multi-denotation. Multi-denotation for overloaded things have the parts, the alternatives, which are denotations. And single denotations can be denotations of symbols. So that's essentially what's stored in a symbol. And they also have potentially a symbol. So that means they either have no symbol or one. And if they have a symbol, then the symbol essentially points to a symbol denotation. And again, that's indexed by the current phase. So that's essentially the whole architecture of the compiler. And what's, I think, important to notice that essentially it's all immutable, and what is time dependent is carefully controlled. It's here and here. Okay, so the lessons learned from this, we're not done yet, we're still learning. It was a great learning experience so far, is think databases or functional reactive programming for modeling. Think FP, functional programming for the transformations, for the micro things. So macro thing, functional reactive programming, micro things, functional programming. Get efficiency through a lot of low-level techniques, a lot of caching, but take care not to compromise the high-level semantics. So how to make it fast? That was, of course, one of the goals, and you could say, well, all this thing looks terribly inefficient, indexing by the phase and all this thing. But nevertheless, the current Dotty compiler achieves at least twice the speed of the current Scala compiler, and I think by the time we're done with it, will be 3 or 4 times the speed of the current Scala compiler. So how do we get that? Because it seems that we pay a big price upfront for going to this very functional, very abstract representation. Well, the advantage of doing that, of going functional, is that you have many, many more opportunities to cache, because values are immutable. So when you compute a value, then the next time that you compute the value, if things are purely functional, it will be the same value given the same argument. So you can memorize the function. You can cache things. And we cache at many, many different points in the compiler by a lot of different techniques. So for instance, the symbols, to go from a denotation to a symbol, it's cached as the last denotation. To go from a name type of a reference to its denotation, again, we have a cache for that. Those caches, they are stamped with a validity interval. So they say, okay, it's valid in this phase up to the next phase where somebody transforms some info. We know that because we essentially have a list of denotation transformers that are also indexed by the phase. And we need to update only if we go outside of the previous validity period. The other important thing is once we compute the member, so that says the denotation of something, given a prefix dot name, and we want to say what does it mean. That's sort of one of the three core algorithms in the compiler. Given prefix dot name, what does it mean? Again, that can be cached. So we can say, well, if it means this thing the last time I've asked and I'm still in the same phase, then it will mean the same thing again. We're purely functional here, so we can cache these things. Okay, so caching has been done extensively, but to very good effect. What we haven't tried yet, that's future work, possibly, is parallelization. So in principle, being very functional should also help you a lot in parallelizing things because, well, essentially we know that that there are less headaches the less state you have and the more controlled your state is. We haven't tried that yet, and it could be hard if it's too fine-grained, similar to chess programs where essentially you have just too many join points of these concurrencies. The other worry is that it seems like our compiler is probably a lot of similar compilers is rather memory bound. That means the bottleneck is not so much the computation, but the memory accesses. And if that's the case, then it really depends on your cache and memory architecture whether parallelism will buy you a lot. So we haven't really done this experiment. Initial experiments are actually not too bad. So it seems that even though it seems to be memory-bound, parallelization could help. But we haven't anything that's functional yet. Okay, going back to caches, the caches actually take many forms. One is simple old lazy vals. So lazy vals add as a cache, but there's also function memorization, and there's LRU caches. So for instance, when we want to find out for a given prefix type, what was the type of this member, if we do this for every member we look for, we might actually get huge caches in the cache table. So we bound the size of the cache to, I think, 8 entries, the last 8 hits that we got. And we have sort of clearly a very hardware-like, at least the last recently used cache here for the member lookups. Another optimization that we did is phase fusion. So you've seen these humongous number of phases. That also is a significant overhead because every phase has to traverse the whole tree and possibly build a new tree where things change. And since these trees are typically large, that typically busts your hardware caches. So you go to plain memory, and of course it takes forever to load these trees in. So the more traversals you have, the worse your memory locality is. And the idea there is that we have fused the phases. So for modularity reasons, the phases should be small. Each phase should be only one self-contained transforms. But what we actually do is we fuse those phases into one tree traversal. And again, that's done essentially in a framework. So it's not done by hand, but essentially you just have a grouping of phases to indicate, I want to group these phases together. And then there's just a tiny amount of reflection to make this really fast, to essentially fuse this all into a single traversal. So that also helped a lot empirically, where we see that if we don't do that, then we get a significant performance slowdowns. So the next steps, let me conclude with that. We want to get more libraries into the community build. Currently we have Scala Check and some others. The big problem with that, and that's the current problem we tackle, is that macros as they exist in Scala 2 will no longer be supported in Dotty. Macros are always very experimental, but that didn't prevent people from using them widely, I know. So it's actually difficult to find libraries that don't use macros and that therefore can be ported easily. Eric was so kind to say he would actually work with us to essentially make Spire macro free so that we could port it. So that's a target I'm looking forward to. The next thing is that, well, of course, macros won't go away completely. That would be unfeasible. So essentially, there will be a new macro system based on inline and meta, which I think Eugene has started talking about in previous Scala Days conferences and other conferences. And the big challenge will be migrating code that uses the old experimental macros into the new inline and meta. So inline is essentially, there's a pull request that was just in the weeks up to this conference. I worked on that, and so inline is basically done, and meta hopefully will be. So just to quick explanation, inline is essentially the inlining thing that pulls things, source from one point to the other, and meta is the meta programming thing that says, well, now let's look at these things in quasi-quotes and things like that. So we decided that it would be useful to split these two efforts into two essentially related concepts, and one half we have. So what I'm looking forward to is actually getting the second half into Scala, which means that people even can port things that have serious use of macros by rewriting them into Scala meta, which they should do anyway because macros will go away. And that way we hopefully get a solid base of community libraries on which people can build, and that will also help get us a real release out that people can use. Okay, thank you.